Welcome to an introduction to chemistry, brought to you by Parkbench Tutors. For more information on Parkbench Tutors, just look us up on Facebook or visit parkbenchtutors.com. In this podcast we are going to continue our look at gas laws, and this is our second part. You should have watched our first part already. So we're going to start by looking at how we convert various units for pressure. We have to convert torr to millimeters of mercury or millimeters to mercury to torr. This is a fairly easy one, since 1 millimeter of mercury is equal to 1 torr. The conversion factor is simply 760 over 760, which means 1. Now, what happens if you want to convert millimeters of mercury to atmospheres? Well, 1 atmosphere is equal to 760 millimeters of mercury. So the conversion factor is 1 atmosphere over 760 millimeters of mercury. So for example, if we take 740 millimeters of mercury and we put that in, plug it in, we get 740 millimeters of mercury multiplied by 1 atmosphere divided by 760 millimeters of mercury. The units, millimeters of mercury, will of course cancel each other out, leaving just atmospheres, so our answer is going to be in atmospheres, and that works out as 0.974 atmospheres. Okay, your turn now. Convert 450 millimeters of mercury to atmospheres. So think about what you've got to do. Right. It's the same calculation, 450 millimeters of mercury multiplied by 1 atmosphere divided by 760 millimeters of mercury. The millimeters of mercury cancel each other out, leaving an answer in atmospheres of 0.592. How about another one? Convert 2.50 atmospheres to millibars. Now in this case we've got a different conversion factor to look at. 1 atmosphere is equal to 1013 millibars. So 2.5 atmospheres will be equal to 2.5 atmospheres times 1013 millibars divided by 1 atmosphere. The atmospheres will cancel out, leaving an answer in units of millibars, and it comes to 2532.5 millibars. And one more. You have to convert 267.50 kilopascals to atmospheres. 1 atmosphere is equal to 101.325 kilopascals, so let's plug everything in. 267.50 kilopascals equals 267.50 kilopascals multiplied by 1 atmosphere divided by 101.325 kilopascals. Kilopascals will cancel each other out, leaving an answer in atmospheres of 2.64. How does the number of molecules influence what's happening with pressure? Well, pressure results from molecules striking the walls of whichever container the molecules are held in. So assuming the temperature doesn't change, the more molecules you are, the more collisions there are going to be, and so the higher the pressure. So pressure then is directly proportional to the number of molecules. Now, the number of molecules we can measure in moles. A mole of molecules is 6.022 times 10 to the power of 23 molecules. At 0 degrees Celsius, 1 mole of molecules exerts a pressure of 1 atmosphere when it occupies a volume of 22.4 litres. It's an important concept to remember. So let's go back and look at moles of molecules. There are 6.022 times 10 to the 23 molecules in a mole. And 1 mole of molecules at 0 degrees Celsius occupies 22.4 litres and has a pressure of 1 atmosphere. So 2 moles under the same conditions will have a pressure of 2 atmospheres, because we're going to have more molecules. And half a mole of oxygen molecules and half a mole of nitrogen molecules under those conditions will have a pressure of 1 atmosphere. And 2.5 moles of hydrogen molecules under the same conditions has a pressure of 2.5 atmospheres. Okay, what about the effect of temperature? Molecules have kinetic energy. And the amount of kinetic energy depends on the temperature. The higher the temperature, the faster the molecules are going to move about, and so the more kinetic energy they will have. So if they have more kinetic energy, in other words, if they're moving faster, the more chance there is that collisions will occur, and so the greater the pressure is going to be. So pressure increases with temperature, providing of course that the gas is contained in a fixed volume of space. And this gave rise to Boyle's law. Boyle was the first person to define this, and he determined a relationship between the pressure and the volume of a gas. At constant temperature, the volume is inversely proportional to the pressure. Right? V is proportional to 1 over P. Volume is inversely proportional to the pressure. And from that you'll see that we derive the fact that P1 V1 equals P2 V2. Okay, here's the Boyle's law expressed graphically. You can see how the volume changes with the pressure, and you can see that as you increase the pressure, the volume is going to decrease. Okay, in simple terms, when the pressure is increased, the volume decreases. When the pressure is decreased, the volume increases. We can say then that pressure multiplied by volume is a constant, or we could write that as PV equals K. So that's where we get our P1 V1 is equal to P2 V2 from. Now remember, Boyle's law only applies if the temperature remains constant. If the temperature changes, then Boyle's law won't apply. Okay, let's look at some problems with this. What will the volume of 3.6 litres of a gas be if the pressure is changed from 760 millimeters of mercury to 500 millimeters of mercury? We know that P1 V1 is equal to P2 V2, and we are looking for V2, so we need to express V2, and V2 will be equal to P1 multiplied by V1 divided by P2. So let's plug in what we've got, and we find that V2 is equal to 760 millimeters of mercury multiplied by 3.6 litres divided by 500 millimeters of mercury. The millimeters of mercury will cancel each other out as units, leaving litres as the units for the answer. We do our bit of maths and we find it comes to 5.47 litres. Let's just take a second one of these, get yourself familiar with them. A fixed mass of oxygen occupies a volume of 44 litres at 800 torr. What volume will it occupy at 4 atmospheres? Now you see we swapped around the units for pressure here, so we've got to be careful. So 800 torr is equal to 800 times 1 divided by 760. The unit's going to be in atmospheres, remember, and it comes to 1.05 atmospheres. Now we can plug these into our equation. V2 is equal to V1 P1 over P2, and we've got all the figures that we need. So 44 litres times 1.05 atmospheres, all divided by 4 atmospheres. Atmospheres will cancel each other out as units, leaving an answer in litres. We do the maths and it comes to 11.55 litres. Okay, let's just have one more and get ourselves into the swing of this. 800 millilitres of a gas at 400 torr pressure are subjected to a pressure that reduces the volume to 200 millilitres. What's the new pressure? Okay, we're looking for P2. P2 is equal to P1 multiplied by V1 divided by V2. So I plug in the numbers that I've got, and P2 is equal to 400 torr times 800 mils divided by 200 millilitres. The millilitres will cancel each other out, leaving torr as the units for the answer, and P2 will be equal to 1600 torr. Okay, your turn now. Let's see if you really followed this. 750 millilitres of oxygen gas at 2 atmospheric pressures are subjected to a pressure that increases the volume to 3 litres. What's the new pressure? Note that we've got two different units here for our volume, so we've got to just work on those first of all, haven't we? 750 millilitres is equal to 0.750 litres. So we can now plug our numbers in. P2 is equal to 2 atmospheres times 0.750 litres divided by 3 litres. The litres will cancel each other out, leaving the units for the answer to be in atmospheres, and if we do the maths, it comes to 0.50 atmospheres. Okay, we're really pushing these, so this should go into heads one sooner or later. A gas occupies a volume of 6.73 litres at 0.45 atmospheres. So at what pressure will the volume be? 7.44 litres. Okay, fairly straightforward here. Both of those are in litres, and we're looking for an answer in atmospheres. So P2 is 0.45 atmospheres times 6.73 litres divided by 7.44 litres. The litres will cancel each other out, leaving an answer in the units of atmospheres. So we do our maths, and P2 is 0.41 atmospheres. That ends this little session with lots of calculations for you, brought to you by Parkbench Tutors and narrated by David Hopcroft. Thank you for watching and for listening. We wish you success in your studies. For more information about Parkbench Tutors, look us up on Facebook or visit parkbenchtutors.com. And if you visit parkbenchtutors.com, there are some courses where you can sign up for a playlist.